The topic is how to secure Kubernetes cluster. We will discuss how is Kubernetes cluster security is managed and how it is secured. But before we begin, hi, I'm Kev. I have been recruiter in the past. I moved into DevOps from scratch. This is part of my transition series. If you are making this same switch, stick around. So securing a Kubernetes or K8s cluster is not just an administrative best practice, it is a fundamental requirement for production environments because Kubernetes orchestrates containerized workloads across multiple machines. A compromise in one area can lead to a full cluster data exfiltration or malicious resource hijacking like crypto mining. Securing the cluster protects the underlying infrastructure, the hosted applications, and sensitive business data. So securing Kubernetes cluster is not just a basic or administrative best practice. It is a fundamental requirement for production environments, meaning it is a really important step and we must make sure that Kubernetes cluster and Kubernetes environment is secure and follows the best security practices. It is because Kubernetes orchestrates or operates between containerized workloads across multiple machines. A compromised or hijacked or malicious attempt in one area of a cluster can lead to a full cluster takeover, that is data exfiltration or malicious resource hijacking like crypto mining. So securing cluster protects the underlying infrastructure like hosted applications, sensitive business data. Now how it is secured? First, it is by securing API server via TLS. The kube-apiserver is the gateway to a cluster. Every administrative command, internal component, communication, and deployment goes through it. If it is unencrypted or exposed, attackers can take absolute control. So kube-apiserver is the gateway to the cluster, and every command, that is administrative or internal component communication and deployment, goes through it. So if kube-apiserver is unencrypted or exposed, so that attackers can take the absolute control. So how this API server can be encrypted or secured or have the security best practice? By default, production clusters encrypt API traffic using TLS or transport layer security. This is enforced by modifying the static pod manifest file for the API server that is typically located at /etc/kubernetes/manifest/kube-apiserver.yaml on the control plane node. So we ensure that specific flags point to the valid X509 certification and private keys. So that is like the commands for TLS certification file, TLS private key file, client CA file. So these are the updates that need to be made in the kube-apiserver YAML file that would have valid TLS certificate. By default, kube-apiserver is not encrypted. So to encrypt it, we must provide TLS certificate inside the kube-apiserver YAML file. By doing it, it would be secured and encrypted. So the difference you can understand it by knowing HTTP is not secured and HTTPS is secured in a website. So HTTPS would have TLS certificate and it is secured. It has also the same mechanism of providing TLS certificate in it. So we are securing kube-apiserver by adding or providing TLS certificate. So the internal communication, every communication or commands that are being made via kube-apiserver is encrypted. It provides transport layer security. So when we modify this YAML file, the kubelet automatically restarts the API server pod to apply the secure configuration. Second is role-based access control or RBAC. Not every user or service needs administrative privileges. Role-based access control ensures the principle of least privilege, meaning users and software applications only get the exact permissions that they need to do their jobs. I've already explained role-based access control in detail in my previous Kubernetes videos. You can also watch those if you want to know role-based access control. But simply role-based access control is providing the required or exact permissions to the users or services to do their job and not providing more than that permissions to have better control and security over our services, applications and its data. So administrator or admin will have all the permissions and rest of the users and services will have permissions only that is needed to do their job. So how it is done? Role-based access control or RBAC uses 4 core components of Kubernetes objects to map who, that is subjects, can do what, the verbs to which resources, meaning role or cluster roles. It is to define permissions. For example, a role might allow a user to only get list and watch pods. That is, cluster role apply, cluster-wide roles apply to a specific namespace. So role-based access control is a concept where we outsource or offload the user management by using the services of OAuth, by providing users information in the OAuth or IAM of the AWS, and then we provide the login for those users that has already been created inside the AWS or other cloud provider services. That was about user management and user being created. But users will also have certain job to do. Like if it is a DevOps engineer, that would have certain role. So role is, you can say, YAML file or a permission file which has certain permissions that can be list or watch pods, and that can be assigned to users so they can have that much permission with respect to the information provided in it. Simply role or cluster role are set of permissions like that defines actions like read, write or delete with respect to a user, group or an application that can perform on specific Kubernetes resources. Role is restricted to a single namespace, and cluster role is cluster wide, meaning it is across all namespaces. Basically, cluster role is not limited, but role is limited to a single namespace. Now, role or role bandings or cluster role bandings. So these are attaching those permissions to specific users, groups or service accounts. Meaning role are the specific roles and permissions in a file. Cluster role banding or role bandings is a step where those permissions are attached to the users, groups or service accounts. So both roles, cluster roles and role bandings or cluster role bandings go hand in hand. Role is like the specific file of permissions, and role bandings is a step to bind those with the users to have better role-based access control. Third is network policies. By default, Kubernetes networking operates on a flat structure, meaning all pods can talk to all other pods across the cluster. If an attacker compromises a front-end application, they can easily traverse the network to attack the backend databases. So in Kubernetes, by default, all pods can talk to all other pods across the cluster. So this is not a healthy or secure step or structure that Kubernetes follows. So if an attacker compromises a front-end web application, they can easily traverse or hack the network to attack the backend databases. So it must be secure and follow certain rules or practices to avoid it being hacked or get malicious attempts. How it is done? Network policies act as an internal firewall for our pods. They allow us to define explicit ingress, that is incoming and egress, outgoing traffic rules based on labels and namespaces. So this pod-to-pod communication or all communication within the cluster, that is networking, is solved by implementing network policies. Network policies is a similar concept to role-based access control, meaning we don't allow the default every traffic or all traffic to be spread across all the namespaces across the cluster. Instead, we only allow specific traffic or traffic based on the labels and namespaces that is only needed for those resources. So that would allow us to define explicit ingress, that is the incoming traffic, and outgoing traffic based on the labels and namespaces we specify in the network policies. So how it will look like? We must use a container network interface, that is CNI plugin, that supports network policies such as Calico, Calium or Weave. So we can use CNI plugin, that is container network interface plugin, that supports this network policies concept. And a standard production strategy is to be implemented by a default deny all policy for a namespace, and then we explicitly write policies to allow only required traffic. For example, front-end pod can talk to back-end pod on port 8080, but back-end pod cannot talk to the front-end. First would be a CNI plugin that supports network policies should be implemented, and also by default we can implement a deny all policy for a namespace for a network, so it would not allow any traffic by default. And then we specify certain rules or certain policies to allow required traffic that we need. For example, if we need front-end pod to talk to the back-end pod on 8080 port, but back-end pod should not talk to the front-end. So we specify these rules or policies in a namespace. So we would be implementing deny all by default. It would not allow any traffic by default. And then we specify certain rules or permissions that we want to have. So it would operate on those permissions. Now fourth is encryption at rest, that is etcd. etcd is the source of truth and the key value database for Kubernetes. It stores configuration data, cluster state, and crucially Kubernetes secrets, that is passwords, tokens, API keys. By default, etcd stores this data in plain text. If an attacker gains the access to the backup storage or the master nodes file system, they get all our secrets. So we know that Kubernetes architecture has certain components, and one of them is etcd, that is like the database that stores key value data, and it stores configuration data, cluster state, and crucially Kubernetes secret, that is password, tokens, API keys, all those data as well. So by default, the data that is stored in etcd is in the plain text. So if an attacker gains the access to this etcd address, hacker can easily understand the passwords that is in the plain text and eventually get the secret or API key information. So how it is solved? We configure the API server to encrypt data before writing it to the etcd using an encryption configuration object. So it is solved by encrypting the data, specifically sensitive data, which is Kubernetes secrets, API keys, passwords, in etcd using encryption configuration object. How it is done? We create a configuration file specifying which resources to encrypt, typically secrets, and the encryption providers such as ACE GSIM or ACE SCBC. Then we pass this file to the API server via this flag. So to encrypt the secrets or sensitive information stored in the etcd, which is like the database for Kubernetes, we can take the help of encryption providers like ACE, GCM or SBC by creating a configuration file and specifying the resources like secrets for it to be encrypted, and then we pass this file to the API server via encryption provider config flag. And for enterprise environments, it is best practice to use a key management service KMS provider like AWS KMS, Azure Key Vault or HashiCorp Vault. So the encryption keys are rotated and managed outside the cluster. And for enterprise or production environments, the best practice is to use key management service that is provided by cloud providers like AWS KMS, Azure Key Vault or other providers like HashiCorp Vault. So they would manage the keys for us, so that keys would be encrypted, that would be rotated outside the cluster, and it is managed by these providers. Fifth is using secure container images. A cluster is only as secure as the applications running inside it. Container images frequently contain outdated operating system libraries with known vulnerabilities, that is CVEs, or worse, that is malware. A cluster is only as secure as the application running inside it, meaning if the application running inside a cluster is not secure, then the cluster will not be secure. So the application running with outdated or vulnerable container images or outdated operating system libraries with vulnerabilities or malware will eventually affect the security of the cluster. Then how it is managed? Minimal base images. We use minimal base images like distros or Alpine Linux instead of full Ubuntu or Debian images. This drastically reduces the attack surface. Or simply we use the specific images or with specific patched or fixed versions that doesn't have vulnerabilities in it. And second is vulnerability scanning. We integrate automated scanning tools like Trivi, Claire or Grip into our CI/CD pipeline, which blocks deployments if images contain critical or high vulnerabilities. I have already made a complete video on DevSecOps image scanning and scanning in general for the application, which is Trivi and all this vulnerability scanning, and I make sure that my application was almost like 99% vulnerability free. Third is private registries and image signing. Storing images in secure private registries and using tools like Cosign to sign images. This ensures that the cluster only pulls verified, untampered images, and we can store the images in the private registries so it is secure, and we can use the tools like Cosign to sign the images, ensuring the cluster only pulls verified, untampered images. Sixth is cluster monitoring and runtime security. Prevention mechanisms like role-based access control and network policies cannot stop zero-day exploits or malicious inside behavior. we need real-time visibility into what is actually happening inside our running containers. So role-based access control and network policies are great in solving a lot of issues with respect to security of the cluster, but it cannot stop day-to-day exploits or malicious inside behavior. We need real-time visibility into what is actually happening inside the cluster or inside the running containers. How it is solved? We use runtime security and observability tools like Sysdig, or that is Sysdig, which is built on open source Falco. These tools hook into the Linux kernel, that is often via EBF, to monitor system calls. They detect anomalous behavior in real time, such as containers suddenly spawning a root shell, changing system binaries, or attempting unauthorized outbound network connections. If malicious activity occurs, the tool triggers immediate alerts or automated containment actions. For real-time security and observability, there are certain tools like Systemd or Sysdig, which is open source. These tools hook onto the Linux kernel, that is the root of the Linux, often via EBF, to monitor system calls or how we communicate with the cluster or the system. They detect anomalous behaviors using AI or other within it in real time, such as containers suddenly spawning in a root shell, changing system binaries, or attempting unauthorized outbound network connections. So it detects or checks the suspicious behaviors real time using certain AI/ML concepts within these applications, that is open source Systemd. So if certain malicious or suspicious activity occurs, this tool triggers immediate alerts or automated containment actions to fix or solve those vulnerabilities and issues that is happening real time. Now, seventh and the final is keeping the ecosystem up to date. Kubernetes moves fast. They release new minor versions regularly. Older versions stop receiving critical security patches. Furthermore, the underlying operating system's container runtimes like Containerd and KTS components accumulate vulnerabilities over time. So, one of the key aspects of keeping Kubernetes cluster secure is to keep everything that is within the cluster and its components, including Kubernetes components, up to date within the patched or fixed versions, that is the latest versions. And with respect to Kubernetes, the Kubernetes releases minor versions regularly, and older versions of Kubernetes stop receiving critical security patches or fixes. Furthermore, the underlying operating system, container runtimes, Containerd, and all these components accumulate vulnerabilities over time. So it needs to be updated or kept up to date by updating or upgrading it. So how it is done? Regular patch schedule, establishing a lifecycle management plan to upgrade Kubernetes clusters systematically, that is control plane first, then worker nodes, then staying within the officially supported versions, that is the latest 3 minor versions, then node operating system patching, that is to use managed Kubernetes offerings like EKS, GKE, AKS to automate node operating system patching, or using automated tool like Cured, that is Kubernetes reboot daemon, to handle safe rolling operating system updates on self-managed nodes without disrupting application availability. So that was about Kubernetes upgrades thing, but we must make sure that other components, Jenkins, Terraform, or other tools that we are using or implementing within the CI/CD pipeline or in general are upgraded or up to date with the latest or near latest versions, so it is vulnerability free. So that is it for the video today. Thanks so much for watching. If you have any questions, do let me know in the comments. Thanks. Have a good day. Bye.